start with this again. What I'll begin with is basically the Box-Jenkins model. Okay. Now, the simplest form of the Box-Jenkins model is the autoregressive model of order P. Okay. In this case, we write yt as a function of its past values. Okay. It's said to be an autoregressive of order P if yt depends on yt minus 1, t minus 2 up to t minus p. There can be a constant involved here, the intercept. I am taking that out because that can always be adjusted. And this epsilon t's, these are generally referred to as white noises. We will come to this epsilon t later on. This is a name that came from the engineers, they called it the white noise. So it's a self-regressed model, and generally we write this as 1 minus alpha 1b minus alpha 2b square, etc. B is a backward shift operator. So what is B? What is B? If I write, can you see me from this from the back? This is too small, I think. Okay. This is xt minus 1. If it's to the power of p, then this would be xt minus p. Okay. So this is another way of writing this model, and I can take this yt, etc., everything on the left hand side, I can write it, and we call this phi b, and this phi z is called the characteristic polynomial associated with this model. This basically is, these are operators, so we just use z here, okay, and this is referred to as the characteristic polynomial associated with this model. And this is important from some point of view, but let's look at the properties. First of all, expectation yt would be 0, and it's a little bit more complicated for yrp, but for the ACF, if I take p equal to 1, then the ACF comes out to be alpha 1 to the power of h. Okay. Now this is important, and okay, maybe I'll start with this. AR1 is xt, I'll keep to the notation, so I'll put it as alpha 1, xt minus 1, plus this is epsilon t. Okay. And okay, so I can write this as, can I write it this way, alpha 1 xt minus, or maybe can I write it this way? Xt minus 1 is what? Alpha 1 xt minus 2 plus epsilon t minus 1. So if I go on doing this, after some times I will have something like epsilon t plus alpha 1 epsilon t minus 1 plus alpha 2 epsilon t minus 2, etc. I can go on to an infinite past. What would be the expectation of this? Xt. This is going to be 0 because all the epsilon t's have 0 mean. Okay, so this is going to be 0. What about the variance? What would be the variance of xt? Yes? These are independent. These are IID, mind you, okay? Let me go back to the previous slide. This epsilon t's would be IID. So what would be the variance? Is the variance of this? Suppose we have a constant variance, so this is sigma square 1 plus alpha 1 square plus, sorry, this is alpha 1 square, right? Alpha 1 to the power of 4, etc. And so what does the variance come out to be? Sigma square over 1 minus, sure, if alpha 1 is, what happens if alpha 1 is not less than 1? It will blow up. Okay, so the variance would depend on t in that case. Okay, you only get this if alpha 1 is less than 1. Okay, so this will not be stationary. You see, this is independent of t. Okay, if it was not that, then you would have had alpha 1 to the power of twice t minus 1 or 1 minus alpha 1 to the power of twice t here. Okay, in that case, this would have been dependent on t. It would not have been stationary. So for the process to be stationary, it is necessary that this condition holds. If you have an autoregressive process, first order autoregressive process, this is not a stationary process for all alpha 1. Is that clear? It is only a stationary process if absolutely alpha 1 is less than 1, otherwise the variance would be depending on t. Okay? Okay, so that's one thing we say that. Now, one other way of looking at it, let me, because I am not going to do the general ARP because it's going to be more complicated, but this would follow from this. How do I write the alpha in, what would be my phi for AR1? You see, I can write this as xt minus alpha 1, xt minus 1 equal to epsilon t, right? This can be written this way, and this can be written as 1 minus alpha 1 b into xt is equal to epsilon t. So my phi b is, or phi z is 1 minus alpha 1 z. Okay? That is your phi for AR1. What is the root of this? What is the root of this polynomial? How do you get the root? Equate it to 0, solve, z would be equal to, right? When is the process stationary? I just told you. When is the process stationary? If alpha 1 is less than 1, you can say it that way. Or you can say if the root is greater than 1. Okay, so another way of putting it is if the root is greater than 1. So you see alpha 1 less than 1 would imply that z is greater than 1. Okay? So that's the language that we generally use, because when you have more than one step, okay? So if you are a general ARP, how many roots would you get? P roots. Okay? And these P roots, some of them may be real, some may not be real also. Okay? So basically what we say, phi z, if the roots of phi z, it becomes very difficult to identify in terms of the parameters. Okay? What we rather do is we refer this in terms of the, instead of looking at the alphas, instead of putting it this way, we put it this way. It's easier to do that. Okay? So we say that this AR process is stationary if the roots are outside the unit circle. Unit circle, we are talking about a circle because we are looking at a argand plane. It can be, some can be imaginary, right? So we are looking at an argand plane, and we say that if it's outside the, if it's real, we'll say that if the roots are greater than 1 in absolute value. Okay, so that's how we generally put it. So remember, AR process, and one other thing, if I do the SCF, it comes out to be alpha 1 to the power of h. Okay, so if you have ACF alpha 1 to the power of h, how would you, if I plot this, how would this look like? It will be damped, decreasing, depending on what alpha 1 is positive or negative, etc. But then this never goes to 0. This doesn't coincide with 0, right? You go on increasing h, I have some values. For very large h, it will be, it's tending towards 0, okay? So SCF is asymptotic to the h axis. But the important thing is that PFCF, we can show that, is 0 beyond point P. Remember this too, SCF is asymptotic to the h axis, PSCF is 0 beyond point P. Okay. Now I'll go back to the PSCF here. So if the SCF does not go down to 0, but the PSCF is 0 beyond 2, what would you say? PSCF, suppose, is this, for the first and the second is significant, beyond that it's insignificant. This one, quite a number of values are insignificant. Okay, maybe the first 4, 5, 6 values are significant, then it falls off. What would you say? Because this becomes 0 after 2, we can say that the process, underlying process, is a AR2. Because what happens here is, I'll repeat this, the PSCF is 0 beyond P. So if you see that the PSCF is becoming 0 at some point, you'd know that it is a process, AR process with order just before the point it becomes 0. Because once, if it's an ARP, then from the P plus 1 point it will become 0. And if you see that the process is becoming 0 at 4, you know that it's an AR3. So the PSCF actually helps you to identify a AR process. The SCF does not. Why not? Because the SCF may continue to be non-zero because it's asymptotic to this axis, so it may continue to be non-zero even for large p, okay, beyond p. Okay. This is one thing. The other process that we look at basically is the white noise, combination of the white noise. This is referred to as a moving average process. And since we are taking epsilon t, sorry, this should be epsilon t minus 1. It's epsilon t minus 1 to epsilon t minus q. This is referred to as a moving average of order q. Okay? And you can again write the characteristic polynomial here in terms of the characteristic polynomial. You can express yt in terms of the epsilon t's, the white noise. And you can see the SCF, and you can see in this case that the SCF is 0 beyond point q, because there will be, what happens if I have a first order MA process, epsilon t plus beta 1, epsilon t minus 1, okay. What is the covariance between yt and yt minus 1? What is yt minus 1? What is yt minus 1? Epsilon 2, right? What is the covariance between these two? This into this is 0 because independent. This into this is 0. This into this gives you beta 1 into variance. This into this is 0 again. So you get something like this. What if I take this as yt minus 2? It becomes 0. So covariance between this is 0. What if I take A? So gamma 1 is this, gamma 2 is 0. What about gamma 3? Everything else is going to be 0. So you see, if it's first order, then beyond gamma 1 everything is going to be 0 from second on, etc. If it's second order, then there will be correlations up to gamma 2, and beyond that it will be 0. Okay? So you see, if I plot the correlations, if I have the ACF, and you see that the ACF is 0 from a point, say from the 5th point ACF becomes 0, what can you say? We can say it's a MA4. It's a MA4 because MA4 will have ACF 0 from points beyond 4. So from 5 onwards it will have ACF 0. Okay? So the ACF actually helps you to identify a MA process. Once you see that the ACF is becoming 0, you know that just before it becomes 0, that's the order of the MA process. AR process is not identified from a ACF, it's identified from a PACF, where again you can identify if it becomes 0 at p plus 1, you know that it's a ARP process. Okay? So this too basically allows you to identify which the ACF and the PACF together as to what the underlying process is. Okay? In this case again, just the opposite. Maybe I think I've got a slide on this. Yes. MA process is always stationary. Okay. AR process is not always stationary. It's stationary only if the roots of phi z are outside the unit circle. Okay. Invertibility you don't really need to bother too much. This is invertible if roots are etc. outside. But the main thing is SCF here is 0 beyond Q. In this case, SCF is asymptotic to the h-axis. So this does not help you to identify the process. This helps you to identify the process. So SCF helps you to identify the order of a MA process. Similarly, if you look at the PACF is asymptotic to the h-axis here and is 0 beyond P for the. So if you look at the PACF helps you to identify the autoregressive process. Okay? So the first thing that you always do is when you look at the stationary process, you look at the SCF and the PACF diagram. Okay? SCF helps you to identify if there is a MA component in it, and the PACF would help you to identify whether there is a AR component in it. Okay? Okay. And very often this is what we land up with. Both the AR component here, it's a combination of both the AR component as well as the MA component. We call it a ARMA model. Okay, this is the usual model, that the original Box-Jenkins model. That's a autoregressive moving average model. It has both the autoregressive and the moving average component. So the two models that we studied before are special cases. Okay? We write an ARMA model as ARMA PQ. P stands for the order of the AR part, and Q stands for the order of the moving average part. Okay? So we call it an autoregressive model if Q is 0, and it's a moving average model if its P is 0. Okay? In general, we can have a ARMA PQ model in general. Okay? Now, this is obviously the same thing. This is the MA component, this is the AR component, and together you can invertibility, stationarity, you can look at it from, as I said, MA part is always stationary. This part would be stationary if the roots are outside the unit circle, etc. Okay? Maybe I'll come to this slide slightly later. I'll skip all this for a moment. I'll come back to all those, but I'll come back to the ARIMA process because this is where you all start with. Okay? We talked about ARMA. Any questions on ARMA? You have understood what ARMA is. Okay? ARIMA is a special case. It's called an integrated ARMA. For a process with trend, we use the ARIMA model. Okay? And the ARIMA model is written this way. Remember, how was the ARMA written? Remember? What's the difference? Can you tell me what the difference between the ARMA and the ARIMA is? The ARMA is this is phi of bxt equal to psi of b epsilon t. And the ARIMA is this will have 3 parameters here, p, d, q. Left hand side is fine. Okay, this is the, let's look at, rather right hand side is fine, it's the same thing. Let's look at the left hand side here. Okay, the difference only is that you have this component here. Okay, suppose I take d equal to 1. What does this give you? This becomes 1 minus b into xt. Right? That means you take the, this becomes what? xt minus 1, which is the difference. Right? Is this all right? Now what are you doing here? Basically, I started by saying that xt is a stationary process, which really means that there is no trend. Okay? If you have eliminated trend and seasonality, you go for an ARMA model. Suppose, forget about seasonality for the moment. Suppose there is a trend. What can you do? I want to fit a Box-Jenkins model. Suppose there is a trend. What would you do? Your original xt has trend. I want to go to the Box-Jenkins model. What can you do?
Taking differences of series.
You can do 2 things. First of all, get trend somehow, eliminate trend, and fit in a ARMA model. Because once you have eliminated trend, you have a stationary process. You fit in a ARMA model to the stationary process. You eliminate trend, get xt, and fit that in. Or else you don't eliminate, you don't find trend, you difference it. Remember differencing, what does differencing do? It detrends the series. So suppose I difference it, then this part actually becomes xt has a trend, if I do this, I can take the trend out of xt and then I fit the ARMA model. Do you get the problem here? So basically, this part is the difference part where you are taking out, if you have not eliminated. Here you have taken out trend before. Here you haven't taken out trend. You are using the difference here in the model itself to take out trend and then fit in the ARMA model. Okay. So basically, I think I'll come back to your problem. If you have a ARIMA 00011, what does it mean? ARIMA 011. It means that there was some trend in it. Okay, you take out the trend by differencing. Okay, so now you have taken a first difference, taken out the trend, and then what did you do? Suppose my original series was xt, I wrote yt as xt minus 1. So my yt is now detrended. Okay, and then what did I do? 0, 1, 1 means now I fit in a MA process to yt, because it's, you see, the autoregressive parameter is 0. Okay, this parameter is 1. So basically it's a first order MA process. I fit a model like this. Okay, so this is your final model. Okay, have you got this? So if this comes out to be 0, what happens? Now suppose I get this. Suppose I get a model like this. What does it mean? AR2 and the series originally is already stationary. You don't need to take out the mean. There is no trend in it. There is no trend. So it's already, there is no trend, and this component you don't need to difference to get rid of trend. You can just fit in on the original series AR2 in this case. Okay, have you got this difference between the ARIMA process and this ARMA process? Okay, ARMA is on a stationary process. If you have a non-stationary process, you use the ARIMA, get rid of, by integrating you get rid of the trend, and then you fit the ARMA. It's ARMA on an integrated process. Okay. Sometimes what happens is that you also have seasonality. Remember, if you have seasonality, again it becomes non-stationary. Okay, so in that case you do a, you do a differencing here also. So it becomes a little bit more complicated model, but you get to what is referred to as the SARIMA model. When do you do a SARIMA model? If you have both trend and seasonality and you haven't taken those out, with the original series you fit the SARIMA, it takes out care of the both the trend and the seasonality and then fits in the ARMA model. Okay. Do you get the problem? Any other model that you can think of? We don't write it, but I'm just asking you. Any other type? You can have something called a SARMA model. If you don't have trend, only seasonality, then you can have something called a SARMA model also. Okay. So these are special cases as to how you do it. That's the reason I told you the classical model. Okay. If you do the classical model, if you get seasonality, trend, eliminate them, then always go for the ARMA. You don't have to go for ARIMA. But if you go straight into the Box-Jenkins without looking at the trend and seasonality, then probably you'll have to look at the ARIMA or the SARIMA models. Okay? Yes?
So we can talk about ARIMA models only if the trend is polynomial in with time, right? So
yeah.
What if the trend is not polynomial in?
It makes things difficult, yes. So basically what you do is, I would suggest that I always prefer the classical method. Yes. classical method, because if you plot it, what happens with the ARIMA model or the SARIMA model, you have no idea as to what the trend is like. But if you do the classical model first, you always have an idea as to how the trend is moving, what sort of a curve you should fit, etc. It gives you a more intuitive idea as to the nature of the model. Okay. Okay, let me go back then. Maybe okay, I think I'll concentrate on this now. I showed you right now that you can write, I just showed you right here. But maybe I just rubbed it out, so I'll rewrite this. I showed you that when you have alpha 1 xt minus 1 plus epsilon t, you can write this as epsilon t plus alpha 1 epsilon t minus 1 plus alpha 1 square epsilon t minus 2 and so on and so forth. This is what? This is a AR1. What is this? Yes? If I write this, it's a, what does it look like? Epsilon t minus 1, t minus 2, etc. It's a MA infinity. So I can always write a AR1 as a MA infinity. These are equivalent models, okay? So I can always, I can always write a ARP as a MA infinity or a MAQ as AR infinity or a ARMA PQ as AR infinity, MA infinity, okay? So these are equivalent, you can go from one to the other, always you can show this. Any questions?
Sir?
Yes.
You said we can write ARMA PQ as a AR infinity and MA infinity. But there is invertibility condition.
Okay, I suppose those conditions hold. Okay, I'm assuming the stationarity, invertibility conditions, everything hold, and I've got this. So any questions? Straight question would be, I'll ask the question then. Why bother with so many models? If you can write one in terms of the other, why, if I can write the AR in terms of MA and MA in terms of AR, why should I define both? Problem is, you see, I can write a ARP as MA infinity. How many parameters does the ARP have? P coefficients. How many parameters do a MA infinity have? Infinite. Okay, so obviously if I do a model, I can't really use this, right? So the important thing is choose a model with smallest number of terms. There would be alternative models. Remember I said identification is not always easy. If you have a ARMA 1,1, infinity you never go to, but ARMA 1,1 would be, you may observe that if you take a AR 14, then it gives you the same result. But ARMA 1,1 has 2 parameters, AR 14 would have 14 parameters, and obviously it will be difficult to explain the AR 14 as well as it will become inefficient because there will be too many parameters involved. Okay? So there would be alternative models because you can go from one to the other. Smaller number of parameters here, a large number of parameters there, those would be equivalent models. But choose the models with the smallest number of parameters because that would be more efficient. Okay? And therefore you are likely to make some mistakes here and there. So you choose the model which gives you the best from a selection criteria. Like you look at the AIC or things like that, and the model that gives you the best selected model, or from that point of view, you can select the model, but there would be always alternative candidates for any time series. Okay? Do you get this point clear? At times this becomes a little bit more confusing. Okay, why should I take this? maybe I can get an alternative for this as 0, 0, 8. Why don't I take this? This too gives me same results. Which one would I prefer? This one. Okay, but the results would be very close to each other because 8 is large. Okay, it's not infinite, but it's large enough. So this might be a good approximation for this. So remember that when you choose models, they will show up alternative models, and you'll have to choose the one which is parsimonious, have the smallest number of parameters involved. Okay. Estimation methods would be least squares, maximum likelihood, Yule-Walker techniques, and they have the Durbin-Levinson, because this can become pretty involved. I'm not going to the methods. AR is simple, but MA and R, because of MA, ARMA becomes at times very difficult. Why is MA difficult? Why is AR easy and MA difficult? Okay, I'll just write this for you and you tell me. Of course you can do that. The problem with studying statistics these days basically is that the software does everything for you, so you didn't really need to bother. You won't have a problem with this, but can you tell me why one is simpler and why the other is difficult? Estimating alpha 1 is much easier than estimating beta 1. Why?
Because we have xt minus 1 data.
Yes. You have xt minus 1, yes.
So based on the data we can estimate.
And what about the second one?
We don't means based on the data.
Yes, I think I get your point. In this case, xt, you regress on xt minus 1. This is the data. And you find simple regression would give you least squares, would help you to get alpha 1. In this case, nothing on the right hand side is known to us. You have the xt series, you don't have the epsilon t series. These are IID random variables. So this becomes much more difficult to fit in. What we do is we use the invertibility condition, transfer this to a AR process of a higher order, estimate the parameters that way. There are algorithms for this, innovation algorithm, and this would all be inbuilt in the computer's programs, so you don't really need to bother. But remember that this is much more difficult to do than this is. For you, both will take 1 second to do, okay? But the theoretical problems are much more in this case than in this case, okay? So these are some of the estimation methods. I'm not going to concentrate on them. Mathematics would be involved. And I'd rather focus on how you apply them, how do you actually interpret these things, okay? Once you have done this, and this I think I should have mentioned this, but since I'm putting it here, I'm going to talk about it here. Suppose I fit in a AR1 process. Okay? After I fit in a process, okay, let's look at it from a regression point of view. Suppose I do a regression here. This is xt and my y is xt and this is x is xt minus 1. I do a regression, I get alpha 1 hat. In a regression, what is the next step that you do? Regression, what do? You predict. Okay, you can predict anyway. But before you do the prediction, something else. You always look at the residuals, mind you. See if there are patterns in the residuals. If there are patterns, you can have several problems, heteroscedasticity, autocorrelation, and things like that. Okay. Now, what would be the residual? An estimate of this. How do you get the residual? Xt minus alpha 1 hat xt minus 1. Okay. So that would be the residual here. So I can write the residual here as Et is xt minus alpha 1 hat xt minus 1. When would you say that this is a good fit? When the residuals are small and you don't really need normal distribution, okay? But what do you mean by normal distribution? A little more generally? It should be random. Random, okay, small variance, random, zero mean. Okay, so you need to check for the, if the model is, what is meant by random here? That means, if this is random, that means once you have fitted this model in, once you have taken this out, this takes out all the assignable part. This is random means you cannot extract any further information from here. Okay, this becomes completely unassignable. There is nothing else you can extract from here. It is completely random. There is no more pattern that you have. If it is not random, what happens? If this is not random, what does it mean? It means there is some pattern that you have not been able to capture in the model. If it's non-random, it means there is still a pattern, okay? So that means you haven't taken a proper model which have extracted everything. If the model is proper, it will extract all the information, leaving whatever is some error, random error, okay? But if it's not random error, there is still a systematic part that you should have been able to take out before. So we check for the randomness of this part, okay? And there are two tests that are generally used, the portmanteau test and the Jung-box test. What you do is you take the random series, ET, etc., okay, and you do the autocorrelations on this. What would be the autocorrelation on the ET series? I have ET, ET minus 1, ET minus 2. If I do an autocorrelation, what would be the autocorrelation here? If it's random, autocorrelation of order 1, 0, autocorrelation of any order would be 0, okay? So what they do basically is, they take the square of the autocorrelation. This would be very small. They will not exactly be 0. This would be very small if this is random. Okay, it's the same, they just use a different divisor that's fine-tuning the whole thing. So they look at this, if this is random, then this Q is going to be very small, and you can do a test for this, use a chi-squared sort of test, and check for the randomness of the series, okay? Is this all clear? Okay? I'll suggest that whenever you start with a time series, you have taken out trend, you have taken out seasonality, then what do? You fit in a ARMA model, right? Even before fitting ARMA model, do a test. Do a test, because if the series is, original series itself is random, you don't need to fit a model. So you can do a test on the original series also if you want to. Start with the original series XT, do a random test. If it is non-random, then only you go for the Box-Jenkins models. Okay? After fitting as soon as you get randomness, yes, you stop. Okay? It can stop even before fitting the model. Do you get my point? Because the original XTs might itself be random, there was no pattern in it. You do a ARMA and you get 0, 0, 0. Okay, that can happen. Okay, so you can check at the very beginning, or then if you don't want to get a 0, 0, 0 here, okay, you can check and then you come back, and if you need a model, you fit the model in, and then you check for the residuals. If the residuals are random, then you can say that you have got a reasonably good fit. Okay. There is a test called Dickey-Fuller test, but this test is basically for unit roots. I said that this must be less than 1. You test whether this is whether the process is stationary, and because Dickey-Fuller I am just mentioning here because it's a test for whether alpha is equal to 1 or less than 1. If it's equal to 1, plus or minus 1, then this is basically a non-stationary process. If it is equal to 1, what did you do? Okay, maybe I'll ask you this. xt is, I'll write it this way, AR1 and alpha is equal to 1, so that I can write this as xt is xt minus 1 plus epsilon t. Right? And this is epsilon t. What is xt minus 1? Xt minus 2 plus epsilon t minus 1 plus epsilon, and this goes on. Say I go up to 0 or maybe 1. I'll stop here. Okay, plus x naught. Okay. What would be the mean? Suppose expectation of x naught is 0, so this mean would be 0. What would be the variance? Again, I'll take this out. What is the variance of this? Yes? T sigma square. So variance depends on T. So can you say this is stationary? No. Usually how do you get the stationary process here? Very simple.
Difference.
Just first difference. You see what is xt minus 1? What is xt minus 1? So that's a random process. That's a random. So first difference will do. Okay? One difference would help here. But the point is, this is not stationary. This is not stationary. Okay? So you need to check whether this is stationary first. And Dickey Fuller actually devised a test for this, and they were testing this alpha equal to 1 against alpha is less than. If it's less than 1, then it's stationary. If it is equal to 1, then it's non-stationary. Okay? And you have this famous Dickey Fuller test, and what they did was they looked at the difference series. So alpha star yt minus this becomes alpha minus 1, and the test they reset this, and they had a statistic like this, etc. So basically this statistic came out to be close. This is not exactly a t distribution, and there are tables, critical points for this Dickey Fuller test. But the important thing is, when would you do a Dickey Fuller test? Okay, forget it for the moment, because you'd rather do this at just augmented Dickey Fuller. Augmented Dickey Fuller test is basically, instead of AR1, they started with the Dickey Fuller test as the AR1, augmented was ARP, and you are now assuming that there may be unit roots in this, okay? And you have the test, etc. If you ask the computers, again the computers would be doing this, but when you do a augmented Dickey Fuller test, at the very beginning, if you have reasons to believe that the process is not stationary, okay, you decide that it will fit in a REMA, okay? When do you fit in a, what would be your D value? If you have a stationary process, the D value would be 0. If you have a unit root, one single unit root, what happens? You take one difference and it becomes stationary. But if you have a unit root, you have to identify that. You can use the ADF to identify if there is a unit root. If there is one unit root, take one difference. If there are two unit roots, if you take out the unit root, you take one difference, you try it on the first difference. Even if there now is another, if it still shows that, the ADF test shows that it's significant, it means there is another unit root. So maybe you'll have to take the second difference. Okay, so the ADF actually helps you to identify how many differences for this D value here you need to take. This is a formal test that you, again most of the softwares have this inbuilt, but if you ask for a separate ADF test, they will give you the ADF test and tell you how many unit roots you have in the model. And If you have 5 unit roots, you have to differentiate 5 times to get rid of the unit roots and then bring the process down to a stationary process before you can fit the ARMA model to it. Okay, have you got this? Mathematics again you can always work out on your own. I think I'll just look at this. I am given x1, x2, xn. I have fitted in a AR1 model. Okay, what would be my xn plus 1 value? I will put a hat because, so I have got a data up to 2018. I fitted a AR1 model to the data. What is my 2019 value? Yes? Alpha hat x of n. I can't predict this, this is random. So on the average this is 0, so I will predict this. What about xn plus? Alpha hat xn plus 1 hat. That means alpha hat square xn. So I can write this as alpha hat square xn. This is how you actually go about doing this. Okay. But I don't have much of a problem here. But tell me something like this. xt is okay, and I want to predict xn plus 1 here. What I can tell you is that when they do this, they get estimates given x1, x2, xn. I can also estimate epsilon 1, epsilon 2, epsilon n hat. Okay, so if given this, what would be this value? Yes? This is equal to what?
Beta 1 hat.
This? I can estimate this, I have got this, so I can put a value to this. What about this part? I don't know this value. On the average this is 0. So on the average I do this. Okay. What about this? I can't do this. I can't do this because this will depend on I don't have this. So don't become too adventurous and go on predicting several steps ahead. You see, you can't do that. You can't do that. Always remember that sometimes you become very adventurous. You have 15 years data and you predict 50 years ahead. You can't do that, basically. Okay? So maybe 1, 2, 3 steps is fine. After that, what it will show is, it will start showing zeros or constants. Like what you got, basically. You started getting constants after a time point, okay? Because you are fitting in a MA model. You had 0, 1, 1. So you differentiate and then you are fitting in a MA model. Therefore, you can't go beyond certain steps. Because the predictors would become flat. It can't predict anything further because it doesn't have sufficient past data to do that, okay? So when you predict, basically, usually the past values of epsilons you will be taking as zeros, or rather the future values of epsilons would be zeros, like I am taking this as 0. future x values by their predictors like I did here, xn plus 1 hat, etc. And all past values of xn epsilon by the observed and estimated. So x, if I have xn, I have this past value observed, and for epsilon, I have the estimated value of epsilon here, so I'll be using those. But as you go into the future, you cannot predict this. You'll have to take 0, so the prediction value would come out to be 0. So be careful when you predict. Just don't believe that since you have got a good model, fitted model, etc., you can just go on predicting as far as you can. You can't really. Okay, everything. The problem, you'll find that it's going to give you constant values. If you look at the software itself, it will start giving you constant values beyond a certain point. Okay. Okay. Okay, this is something I did. Now I'll come to something else. I had been talking about the mean stationarity. Okay. I've been assuming that epsilon t is 0 mean and variance sigma square. The variance does not depend on t. Okay. Sometimes we have models where the variance is changing. There is changing of variability. So it's a non-stationarity not because the mean is changing, but because the variance is changing. Okay. So we have a changing variance problem. Okay. So xt is the observed time series, predicted value is this. We assume that this is constant, but is this assumption plausible? This is something that started in the 1980s with a very famous paper by Engels that came out in 1982. In fact, for his work on this, he actually got the Nobel Prize, okay, for getting the arch and the Garch models, etc. So that's where it started in the 80s. So after they looked at the Box-Jenkins model, you get the errors. You are assuming that the errors are 0 mean. It's fine because you're testing for the randomness. But is the variance, is there heteroscedasticity in the model? Okay, is the variance same? That's the question they started asking. And the reason they did ask for is because of the, primarily this problem came from stock prices. And you'll see that the stock price, this is the Microsoft stock data, and this saw that this is the type of graph that you are getting. Okay. What it says is that if you look at this part, the variability here is much more. Okay, changes here are much more. In this part, it's more or less close to the mean level. Okay, so the variability here is much less. So you have periods of high variability, you have periods of low variability, again high variability, etc., etc. Okay. So whenever generally, again stock markets, why stock markets? Because stock markets are very susceptible to various changes. For example, we had the election results yesterday, and the stocks either can go up very quickly or go down very quickly. Before every budget, before every election, they start fluctuating like anything. Okay, so again, in normal periods, the fluctuations would be much less, normal times. Okay, so we cannot really assume that the variance for this is constant. You see, the mean level is the same. So we can assume that it's mean stationary, but it's no longer variance stationary. Okay. So can we model this? That was the question that was posed. Okay. And the type of model they are using here is, so it's something like this. We are assuming, I think I can skip this slide because I just said this. We are assuming that the variance unconditionally is this, and the conditional variance is constant. But will predictions be better if the conditional variance is also modeled on the past? Okay. And they tried various models. So you use exogenous information, bilinear models, and ultimately this is the model that has become very popular, the conditional heteroscedastic models, Arch, Garch, and now I think, I don't know, maybe 100, 200 odd variations of this Arch, Garch models. That the E-Garch, M-Garch, I-Garch, you name it, and with almost, they've run out of alphabets, I think, now. Okay, so there are various variations of this model. I will give you one or two examples for this later on, but let me stick to the arch model. So firstly, they started with the exogenous information. Xt is epsilon Wt. I am assuming that this is mean stationary, epsilon T Wt minus 1, and you can show that the variance becomes sigma square Wt. So it depends on Wt, it's random depending on this, but this is exogenous information. Where do we get this from? That's a question that, so it's another series that you will have to find, and it sometimes becomes difficult to do this. So they didn't stick to this. They started with a bilinear model where they said that xt depends on this, and you can show that the variance becomes this on the past value of x itself. Problem with this is unconditionally this variance is either 0 or infinity, okay, and that is something that nobody liked. Okay, so what they came up with is the arch model. Okay, arch model is xt is mean stationary, okay, and then you write xt as epsilon t and sigma t, and for the arch p you use a model like this. So xt square, this is the variance, it's modeled on the square of the past values of x. So it's xt minus 1 square, xt minus p square. Mind you, it looks similar to the autoregressive model. So that's how the AR came, basically, autoregressive condition. But instead of xt, it's being regressed on the squares of the values. Okay, so these are squares, mind you. So these are regressed on the squares of the values, and as before, epsilon t is a sequence of I random variables with 0 mean and variance 1, and very often it's taken to be normal, but there are conditions where you don't take this to be normal. There are certain conditions on this, but stick to this part of it. What we are doing is we are modeling xt with this variance is sigma t, and sigma t square is being modeled with the past values of the squares of the observations. Okay. And I'll just look at an arch model. Xt is epsilon t sigma t, so arch model will just be of order 1, this, and you can show that the variance of this model is sigma t square. So this depends on t, and sigma t depends on what. So the past value is high, okay, or maybe I'll come to that in a moment. But remember that the unconditional variance again is a constant, okay, so that doesn't violate the problems there, okay. So it's only the conditional variance that we are looking at here, okay. The process is leptochaotic. These are some of the remarks that I'm putting in. I'm not going to show you the mathematics of this, okay. Maybe I'll just go back here. Conditional variance is sigma t square. Sigma t square is this. Okay. What does today's value depend on? How much variable today's value is going to be like will depend on what the observation yesterday was. If the observation yesterday was large, that means you have a mean level. The observation is either very large or very small compared to it. On either side, it's away from the mean. Okay, I'm taking mean to be 0 here. So if the mean is 0, if it is very much away from the 0 value, then you have a large value of xt minus 1. What does it mean if it's very much away from the mean level? High variability. Okay, high variability. Okay, so if yesterday you had a value which was away from the mean, what is going to be today's value, today's variance? Today's variance would be depend on the square of that value. So if yesterday's value is close to the mean, today's variance would be small. If yesterday's value was large, today's variance is going to be large as well. So when you are predicting, basically, the variance can be predicted on what happened yesterday. And whatever happens, whatever you observed yesterday, you take that into account. You are not assuming a constant variance. Yesterday, if the values were close to the mean, today's variability is small. You say that the model is, or the market is stable in that case. Yesterday's value were far away from the mean, the market was volatile, today's variance would be high compared to that, okay. So that's how they do it. So in arch 1 this, and in arch P in general, you look at the past values, maybe the past 4 or 5 days, and you see how the values have been changing over this, and you model your variance. So as the observations goes on changing, so does the variance. It's a changing variance model, okay. And the problem with this model is that it's generally, you can show that the process is leptocartic, okay. What is leptocartic? Okay, I've got that written in this board, okay. But usually, how do you look at leptocartic? Higher the peak, okay. But remember, if it's higher the peak, it's sharper, so there is less value in the middle, and there are fatter tails. So usually we talk about fat tails, okay. And I'll come back to this problem in a moment, because why is this important? I'll come back to, I just discussed this. For a first order arch, a large observation leads to a large variance, okay. And obviously it's confined to one period. If it's arch 1, pth order arch, it will be confined to p periods, okay. And since you are taking the square value, okay, this is also important. Since you are taking the square value here, okay, positive and negative shocks, that means positively large or negatively large values have the same impact, okay. Sometimes this is disputed, and I will come back to this later, but positive and negative shocks would have the same effect because you are taking the square values here, okay. How much time do you have? Okay, 25 minutes enough. So how do you estimate the parameters? The arch parameters would be alpha naught, alpha 1p. You assume that this is normal usually. You can write the likelihood function and the conditional likelihood, etc. Solve, I am not going to this. So this looks involved, but you can do the usual, again, why am I talking about this? Okay, you can use the Newton-Raphson method, etc. But again, the softwares would do this for you. You didn't bother about this. But basically, you use the Newton-Raphson method, use the max likelihood method. But importantly, the reason I wrote all this out is, okay, you can skip this one here. Very often, okay, I started with the normal distribution. You have the likelihood written down in form of the normal distribution. But remember, as I said right now, it's leptocartic. A normal distribution is mesocartic. Okay, so very often if you are fat-tailed, the t distribution usually gives you a better fit. So if they ask for a choice, estimation generally should be using the t. Okay, so you write the likelihood again. It's the same way you do it for the normal. Okay, the mathematics would be there, fine. But remember, usually volatility models you estimate using the t distribution rather than the normal distribution, because it leads to leptocartic distributions. Okay, it's not a mesocartic distribution. Okay, that's something you should be noting. Alternative models would be sigma t can be e to the power of, variance is positive for any value, but again infinite variance problems. You do this should be xt minus 1, sorry, it's not xt minus 1, but x of t minus 1. So rather than taking the square, you take the absolute, and has finite variance, everything is fine, but working with modulus is not generally more difficult, therefore we generally take the square. The same reason we look at the variance rather than the mean deviation. Okay. Okay, so I think this is something you should be careful of. Given a time series, so what are the steps? Remember what are the 3 models I talked about? First thing that you do is model the evolutionary component. The trend, seasonality, get rid of that. Then you look at the mean stationary. That means you eliminate this and then go for the Box-Jenkins type of model. Okay. Once you have fitted the Box-Jenkins, that is, you have taken care of the mean part of it, take the residuals and then fit in the volatility. And after you have fitted these 3 parts, you need to reassemble them before you can go for the prediction. Okay? And very quickly, so you start with this yt is mu t plus xt, where mu t is the mean of the process. Take account of the conditional, it's necessary to estimate, eliminate the effect of the conditional mean. So first step, use the AR or the ARMA model, get rid of this mu t, yt minus mu t. That is the residual series. Okay, so you have taken care of the mu t by the Box-Jenkins model. You look at the residual series, and then you look at the serial. You remove any serial. You look at the variance of this model. Model the variance using the arch or the Garch model. Okay, I'll come to the Garch in a moment. How do you test? Sigma t square. Okay. How do you calculate variance in general? After all these statistical classes, I am asking you, how do you calculate variance, right? Yes. Variance is 1 by n summation, I'll use this, t equal to 1 to n, xt. Suppose I have 0 mean. Xt square, fine. This would be the a variance of x, maybe I'll just put it this way, right? Now if I just have one observation, I can't calculate the variance. All statisticians would tell you that, okay, you can't calculate the variance, but I want some estimate for this sigma square. How do I do that? Yes? I'll try taking n equal to 1 here. If you take n equal to 1 here, what happens? It's going to be very crude, but what happens? You just have one value here. So basically what you land up with is x1 square only. So when I don't know my sigma t squares, you see these are unknown. These are variances would be unknown generally. Okay. So the only thing that you can do is take an approximate value. This is taken as a surrogate for sigma t square. Okay. So what we do is, you see, the arch model or had sigma t square is equal to this, right? I didn't know my sigma t square. I don't have the value. Instead, you take xt square as a surrogate for this. Fit this regression model here. Okay. Check if alpha 1, alpha 2, alpha p are 0. If alpha 1, alpha 2, alpha p are 0, what happens? What did you say? Your variance is equal to alpha naught, which means it's a constant. So there is no heteroscedasticity. So you do a test for this. Alpha j's are equal to 0 for j equal to 1 to p, and usual f test would tell you whether there is station. So if this is accepted, you don't really need to bother. You know that you have, in the previous step, you have random errors with 0 mean already, and now you know that the variance is constant. But if some of these alpha j's are non-zero, you have to go for a arch model. Okay. Okay, so step 2 would be to identify the arch order. How do you identify the arch order? Okay, I've got this written out here, but don't look at it. What is the arch model? Sigma t, it's an AR model, okay. So except that instead of xt, you have xt squares, okay. So you just look at how do you identify an AR model? You use the PSAF. Okay, so use the PSAF, but not of xt, of xt square. Use the PF of xt square, and you just exactly the way you do the AR model, using xt square, you do the same method and identify the order of the arch. Okay, and once you do that, you can use, I just told you how to do it. Usually you take the t distribution, estimate the parameters, and then you can get the residuals, etc., predicted values, sigma t square, etc. You can check for normality or TT from the QQ plots, etc. So this would be the second step. And forecasting would be, so sigma n square, forecasting would be sigma n plus hat, you have these values here. When you go to the next one, sigma n plus 2, it depends on n plus 1. You don't have n plus 1, so instead of n plus 1, you use this, but from xn, you have the past values, so you can go on predicting the value. So whenever you predict x, what is going to be the next value? What is going to be the 2019 value? Always they will ask you, what will they ask you? Whenever you give an estimate, what is, nobody asks you, but generally people don't ask you. What do statisticians ask you? They will ask you for the standard error. They will ask you for the, even for the, if you predict, they will ask you for the prediction. Other people have problems with what to do with the standard error, but the standard error actually tells you how much away you can be, basically, from the actual value. Okay, the smaller the standard error, the better. So in this case, when you predict 2019 values, they will ask you for the standard error, and the variance would be basically predicted by, given up to 2018, 2019 value would be this given from this. You know that you have estimated this, you have got the past values, you can say the standard error would be dependent on this variance here. So you can speak of the standard error changing, so even the standard error would not have the same sigma square for all steps. It will be changing from step to step. Okay. This is an example. This is the original series they had. Then they mean corrected, they actually difference this, got this series here, and then they, and then they were looking at the returns, square of the returns, and they showed that this is the returns. You can see that this is mean stationary, but when you square it, you can see that there are spikes, and the spikes actually tells you that there is volatility in this model. Okay, the variance cannot be assumed to be the same here as well as here. Okay, so you need to fit a, so first from this you have done the ARMA part, now you check for this and you see that there is volatility, you go for the arch part. Absolute value, as I said, that instead of squaring, you can take the absolute value, and this emphasizes that there is some variability in the, or the variance is no longer constant here. Okay, so the Garch is a extension of the arch model. Arch was this part, Garch is, it's slightly, the names are slightly different, but in this case sigma t also depends on its own past values. Okay, so it's something similar to the AR2 ARMA process. Okay, it's one part of this is xt minus 1, the other part is sigma t minus 1, etc. Okay, and this is a generalization of the arch model, because sometimes they saw that the arch was not giving a good fit. So when they actually, so in this case what happens is that if you look at this carefully, maybe I think I have the Garch 1, yes, look at this model here. Okay, I said that the last value, if the last value is large, then you can expect a large sigma t now. Okay, large value is not large, but the large variance was large. Even then you get a large, so if yesterday was either a large value, or if yesterday was volatile, but the value came out to be not normal, okay, today you can expect volatility again, because yesterday was volatile, today it's likely to be volatile. Yesterday you had a large value, today you are going to get a high variance. Okay, so it depends not only on this component here, it also depends on what has happened, the volatility yesterday. Okay, so it's a generalization, and this also, this generally is gives you a better model like the ARMA instead of the AR. Okay, and the procedure is absolutely similar. And then you have the I-Garch, as I said, the variation of the arch model. The I-Garch, it's basically a integrated Garch model, they call it. So there is a unit root, etc., and you get an integrated model 1 minus beta 1, etc. You have a M-Garch model, okay, and more importantly, you have, I think, this E-Garch model. E-Garch basically, in this case, allows asymmetric positive and negative effects. You see, you take this absolute and this part as the original variable. I'm not squaring this up. So what does that mean? Sometimes they say that positive shocks have a different effect than negative shocks. What we were assuming is that if I square it up, both positive shocks and negative shocks would have the same effect. In this case, they said no. Maybe positive effects and negative effects would be different, and therefore they have variants of this. So as I said, there are, I don't know how many different models they have landed up with. Okay, almost every week they come up with a model, a variation of the Garch model. Okay, so these are some of the references. Okay, you can look at the references. These are the papers I was talking about. This is the 82 paper. Engel started it, and one of his students, basically Bolesev, actually did the Garch model. This is the Arch model in 1984, 4 years later, and there are several discussions of this. Okay, yes, that's all. Any questions now? Yes. 6 o'clock, it's a bit late in the day, okay? Okay, you're free to, okay.
I just have one question.
Yeah.
If you go back to in the slide where it was